In Chapter 1 and 2, we experiment that a good way to reduce overfitting is to regularize the model. Adding hyperparameters to the model makes it less flexible and reduce overfitting. Now it's the time to explore what is actually happening under the hood. For the linear model, we can reduce overfitting by constraining the model weights. We will examine 3 regularization techniques: ridge regression, lasso regression, and elastic net. First, let's take a closer look at ridge regression. Ridge regression is often called L2. In ridge regression, a regularization term is added to the cost function, summing up the squared values of the theta parameters. When using gradient descent to minimize the cost function, this regularization term forces the model to not only minimize the MSE, but also keep the model weights as small as possible. The hyperparameter alpha controls the strength of the regularization. If the alpha is set to 0, ridge regression behaves like a standard linear regression. If alpha is very large, all theta values approach to 0. Let's experiment the different alpha values to observe how the linear model behaves under the various regularization strengths. This is a ridge gradient formula. We have seen this code many times for generating random x and y near a function. We define a linear model function with various alphas. For each alpha, the model fits the training data and generates y new based on x new. Ridge parameters include the ridge penalty for training the linear model. As we can see, with the increased alpha, theta 1 gets closer to 0. Let's try another example with polynomial regression. We use the same function but introduce a pipeline to transform the input data into a higher degree dataset. After the transformation, some input values can become very small or very large because applying the power of 10 on a small or large number can drastically change its scale. We have learned that the model performs best when feeding well-distributed data. To achieve this, we use a standard scalar to transform high-degree polynomial features into a well-distributed, standardized dataset. We discussed the data preprocessing and pipelines in Chapter 2. As a result, alpha has similar effects on polynomial regression. When alpha increases, theta trends towards 0. If we set alpha a very large number, theta value becomes very small, and the polynomial line becomes like a linear line. For ridge regression, we can use either a closed-form solution or stochastic gradient descent to calculate the optimal theta by minimizing the ridge regression cost function. The closed-form formula is used in this part of the code, while the other part implements stochastic gradient descent to calculate theta. Now, let's check out another regularization version of linear regression, Lasso regression, also called L1. Here is the formula for Lasso cost function, which adds the absolute values of feature weights as a penalty term. The gradient of Lasso cost function is also shown. It is hard to understand how Ridge and Lasso behave by looking at the mathematical formula. The following code tracks each update made by the gradient descent. By plotting the theta path, we can understand how Lasso, Ridge, and different alpha impact the optimization path of theta. Let's jump into the code. We will use a batch gradient descent algorithm, which helps us find the best theta value that minimize the cost functions for both Lasso and Ridge regression. Let's examine the behavior of Lasso and Ridge. The function takes an input x containing 3 data points. If we randomly initialize the theta parameters and apply batch gradient descent on x, after certain iterations, we can recover theta values to their original values of 2 and 0.5. You can initialize the theta with any values. Here, we will use 0.25 and -1 as an example. This part of code follows a typical batch gradient descent approach. The key difference is that we have added the gradients for both Lasso and Ridge. Since we already covered batch gradient descent in Chapter 3, we won't go into details here. We can control the gradients by adjusting the L1 and L2 parameters. If L1 equal to 1 and L2 equal to 0, the gradient is Lasso. If L1 equals to 0 and L2 equals to 1, the gradient is Ridge. If both L1 and L2 are set to 0, the gradient is mean square error MSE. Each update is recorded in the path array, so we can visualize the optimization path. The MSE path is stored in the path variable. Another variable stores Lasso regression with alpha equals to 1, while a different variable stores Lasso with alpha equals to 3. Similarly, Ridge regression paths with alpha equals to 1 and alpha equals to 3 are stored separately. This part of the code simply plots all paths on a graph. The batch gradient descent algorithm helps adjust theta from 0.25 and -1 back to 2 and 0.5. The green and blue lines represent Lasso as the cost function. As you can see, the gradient descent decreases theta 2. In our case, after theta 2 becomes 0, the gradient rolls along the x-axis and bounces around at the global optimum. The blue line represents a larger alpha. If we further increase the alpha, both theta values tend toward 0. Now let's check out Ridge regression. There are two major differences compared to Lasso. First, Ridge regression retains both theta 1 and theta 2, whereas Lasso regression completely eliminates some features. The gradients decrease as the parameter approach the global optimum, meaning Ridge converges faster than Lasso. In contrast, Lasso tends to bounce around at the global minimum. We can improve Lasso converge by using a smaller learning rate or gradually reducing the learning rate over time. You can experiment with different learning rates to observe their effects on Lasso convergence. The elastic net regularization term simply mixes both Ridge and Lasso. This is a cost function, and we can update parameter r to control the mix ratio. We can totally add another parameter r into the code and turn the gradient descent into elastic net gradient. So far, we have covered 4 different cost functions: MSE, Ridge, Lasso, and the elastic net. Which one should we use for linear regression? In general, it is best to include at least some degrees of regularization. Ridge regression is a good default choice. But if we suspect that some features are irrelevant, elastic net or Lasso may be a better option. Because Lasso can behave unpredictable when the number of features is much greater than the number of samples. It may select too few features or produce inconsistent results. Another approach to regularize learning algorithm is early stopping. The idea is simple. We train the model iteratively on the training set while tracking the validation error. Initially, the validation error decreases as the model improves. However, after a certain point, the validation error starts to increase due to overfitting. Instead of training for a fixed number of iterations, early stopping allows us to stop training as soon as the validation error reaches a specified value. This is the end of this video. Thanks for watching. If you found this video interesting or learned something, please consider like and subscribe. See you in the next video.